Yeah, my name is Blake Gonzalez. I'm with the HPC group. Tim asked me to be here today. He couldn't make it. He had some prior commitments, so I'm not as boisterous and as fun as Tim, but I'm here for just a second. So I'm an HPC computer scientist at Dell. I formerly came out of the defense and aerospace industry and work in the HPC practice at Dell. And we've gathered together some of our customers who have some of the biggest challenges with power and cooling, some of the innovative techniques that they've used to solve a lot of these problems. So we have Dr. Henry Tufo, who will be speaking about his experience at the University of Colorado with some of the container solutions that we've put together for them, and some of the great success that they've had. Dr. Tommy Minyard from Texas Advanced Computing Center, some of the tools and techniques and challenges they have with power and cooling, and some of the ways they've overcome some of the obstacles. And then also, also, we have Steve Jones from Stanford. They have a large GPU installation there, and some of the power and cooling things that go with GPUs, as you know, with density comes those kind of challenges. So you're here to hear from them today, so I'm just going to leave it to them, and we'll proceed from that point. So, Henry?
So thank you for inviting me here to speak today. A little last-minute change in the title. The SC11 Program Committee objected to me having the same title as what I submitted for the academic work. So to be clear, this is not an academic publication. This is, in fact, our experiences working with Dell to build one of the largest HPC clusters in a container worldwide. I'm Henry Tufo. I'm from the National Center for Atmospheric Research, where I run the computer science section, and I'm a scientist, and then at the university I'm a professor and director of the Computational Science Center. So I just wanted to give, basically this is an experiential talk. I wanted to give an overview of what we did at the University of Colorado, the kind of challenges we faced, and then of course our solution to those challenges, which I think is quite unique. So our objective was to deploy a large supercomputer top 50 style system at the university to support a broad range of research. Our mission from the Vice Chancellor of Research was to support everybody, but obviously you focus on your main pillars. This is life sciences, biotechnology, earth system science, and then energy and renewable energy. Those were our three main pillars. But we reach out to the entire HPC community on the campus. The challenge that we faced here was that the university simply did not understand how to dissipate 350 watts per square foot. They didn't understand the facility challenges that were required here. When the CTO realized this, we had to go back to the drawing board to figure out how to accommodate such a large cluster on the campus in a facility. We had some severe constraints. I mean, his original plan was simply just not viable. We had some constraints. This was money provided by the National Science Foundation. So there was a short time horizon on this. We need to get something in place in a year, and for those of you who work in an academic setting, getting anything done, especially when it involves facilities, in less than a year is close to impossible. Also, there's a fairly substantial green initiative on campus, and on many campuses these days. What we had to do was to show that, in fact, made some strides towards achieving their goals. These are relatively nebulous, of course, so you have to make the argument this is, in fact, a green solution, that it's can be deployed on campus and make that case for them. And then finally, it had to be cost effective. There just simply is not a tremendous amount of money on campus these days to support new buildings, new construction, in support of HPC equipment whatsoever. So it had to be cost effective for the campus to deploy this. So given the time constraints, this basically ruled out doing any new construction, which has a timeline of order years. It ruled out actually renovation, the cost issue primarily, as well as a timeline. Ruled out doing a renovation on existing facilities, as cost to do something at the university is about 3 times what it costs in the real world. If I want to go put a roof on my house, I can expect to pay about 3 times that at a university to get that done. So a combination of those things basically pushed us into creating something that was new in terms of containerized solutions. And basically we leveraged rapid deployment technologies to build and test offsite a fully customized prefabricated data center. And that's what I want to talk about today. The system itself, just to give you this sort of the scope of what we're trying to deploy, it has 342 Dell C6100s. These are 4 2-socket blades in a 4U chassis. It's all Intel Westmere 2.8s, 4 flops per cycle per core, 6 cores per socket, and 2 sockets per node for a total of 134.4 gigaflops per node. You add this all up, there's a total of 1,368 total compute nodes for about 16,416 cores. When it came out, it was number 31 on the top 500 list, which was two Junes ago, and achieved a reasonable percentage of peak on LinPack for what it's worth, around 90%, 86%. So that's the scope of the system. Whoops, I'll go forward. And just to give you an overview, so we went with an APC Epsilon modular solution. This is fabricated to order. These are not pre-configured containers. We found when we started doing the analysis in this space, we went through all of the potential solutions from HP and from Sun, et cetera. We looked at those solutions, found them to be inadequate in a variety of fashions, primarily in terms of expansion, but also in terms of how easy it was to work in the containers, to maintain, to operate the equipment, to expand that over time. And so we focused on building something that looked more like a building. So we used sort of canonical Lego building blocks to build up a 60 by 40 foot building. Each of these, and I'll show you the pictures that go through this, but it basically used that to build what looks like a standard machine room. We did it in a fraction of the time. And in sort of time commensurate with the project itself. So, as I said, these are fabricated to order, to about 3-month turnaround time. So from the time we decide, here's the footprint for our system, here's the dissipation constraints that we need to satisfy, and here's how much of the equipment itself there is going to be in there. About 3 months turnaround time to actually having a pre-configured data center designed and built for you. Our target was a 2 megawatt feed coming into the center, of which we have about a 600 kW footprint that's currently used. So there's plenty of expansion space in terms of the power envelope. In terms of what the floor, just given the square footage, what we can possibly put in this container, it's about a megawatt, maybe a little over a megawatt is the maximum at about 300 watts per square foot load. We decided not to spend as much money on the UPS. We just provided UPS to those portions of the system that needed to retain state. So, for instance, the storage system, login, and administrative nodes. Cooling is a 337-ton chilled water system. It has a variety of modes, including an evaporative cooler and a free cooling plate. And the target that we designed this for was a 1.2 PUE, power utilization efficiency, on an average annual basis. And okay, so and more on the PUE. So getting this required a sort of an iterative process between designing the system and then designing the facility itself. And really getting down to 1.2 and less was really an effort of this sort of co-design process between the two pieces, where we looked at the engineering implications for the specific hardware, but also the implications for a variety of cooling systems. And it also sped up the time it took, the amount of time we had to spend on the particular project, and I'll go through that in another slide to show you how it made efficiencies in the total project deployment itself. And there was a tight feedback loop between these system design facility questions and allowed us to sort of overlap the key technical personnel on both sides, the engineering side, facility engineering side, as well as the system administration, system engineering side of the house. And by selecting and properly sizing these facility parameters, we're able to match this hardware and come up with a PUE of 1.2. As I said, there's more cooling modes in this, but this is the primary 4. This covers a majority of the hours in the year. The free cooling mode, which operates at about 1.05 to 1.1 PUE, which is what we're in for the majority of the year. And then a pre-cooling mode that operates between 1.1 and 1.2. Mechanical chillers with pre-cooling is 1.15 to 1.25, and then just the chillers themselves, 1.25 to 1.35. To date, since we started measuring in January, we're about 1.1 as an annual PUE. So some design decisions, just to give you a flavor of the kinds of trade-offs that we made by coupling these heat rejection with cooling in row form factor. We were able to, in a hot aisle containment system, we were able to eliminate mixing and thus maximize coil differential temperatures on the air side and minimize fan horsepower. We were able to there also use elevated coil aisle temperatures to increase the supply chilled water temperature and extend the differential on the water side to 16 degrees Fahrenheit, which also allows us to reduce system pipe size and pumping horsepower, etc. And then this elevated chilled water temperature also allowed us to maximize the number of free cooling days. So just to give you kind of an example of things, but there were drawbacks to this, of course. This required us to increase the total amount of coil surface area, increasing the number of crack units by 8. So these are the kinds of, just sort of the flavor, the kinds of trade-offs that we had to make in the design process to figure out how to drive the PUE down to our target of 1.2 or less. And the other piece to this particular project is the ability to line up the two components. One of the critical things that we were able to do is it took us about, it takes us about, on average, about 3 months to design a cluster from end to end, to build it, to procure the parts, put it together, and do the initial testing. This doesn't include the acceptance testing or anything like that, but this is just to acquire the parts, design it, put it together. So there are about 3 months of time to do that for our team. And I think this is, fairly standard, experiences out there. But one of the things that we were able to do is we were able to cram the engineering component of this into the same 3-month period of time in that process. So the technology out in industry allowed us to go ahead and do the engineering work, all the design work, in also a 3-month period of time. So literally, these two projects were ongoing concurrently. The container itself was built up in Canada by Epsilon. They did the pre-testing, they assembled the entire building, did everything up there. Once it had passed all their tests, they chopped it and sent it in the United States. And as I said, that process from beginning end to getting the engineering documents to actually fabricating each of the container, the modules inside the container itself, took about approximately 3 months to get to the United States and be delivered. Same thing for the cluster. We basically ordered all the parts through Dell. We did a design and build out in one of Dell's partners in Austin, Texas. And that process also took about 3 months to acquire and test the system and do our first HPL runs, which was the result of which resulted in our first LINPACK run in June of 2010. And then 1 week to ship, where I learned a lot about interstate transportation issues and heavy loads. And then a pretty straightforward timeline after that, about a 1 week to assemble the system, the primary facility integration, and to finish the assembly. About another week to do all the plumbing, because everything has to be reconnected. All the pipes have been cut. They need to be reconnected and reattached. The hot aisle construction, so that needs to be put into place. And then it takes about a week to cable it, and then about another 2 weeks or so to do testing, and then there was contractual acceptance testing. So, I mean, but the key part really is being able to condense both the facility component as well as the cluster component into 3 months, which is, from my perspective, from a project management perspective, was a huge win for our team. Just to give you a picture, it looks like just like any other data center you would normally see. You have 2 hot aisle containment systems. The blue C's are the crack units. We use a full width in-row crack units, and then overhead cabling, etc. for everything. There is a raised floor, but the raised floor is primarily for disaster mitigation. In case there's a leak or whatever, there's 4 drain holes in the bottom of this. And then a standard mechanical electrical room, power distribution panels, and then pumps and chillers and everything. So, but standard size, I mean, reasonably sized facility, about 60 by 35 feet for the facility. And if you walk in there, it looks like just like any other data center in terms of raised floors, tiles, etc. Just a schematic of the engineering diagrams that APC Epsilon put together, and just some pictures of what it looked like up in Canada. There's sort of the canonical ISO-sized frame that was used to build each of these Lego bricks, and then you can see them building out. This is one of the backside of the mechanical facility. And what the nice thing about this is it really reduced the university's role to pouring concrete, running 4 copper wires, of course your fiber river, and then dry well and water, I think a three-quarter inch water line to this, which really simplified the impact on the university itself in terms of what they had to do. And this is just the, just the outcome of this whole process. And just to give you a picture, this is the finished slab. You can see the power coming up. There's 4 drain holes in here. All the cabling, fiber optics comes up on the outside. And then everything comes disassembled. It needs to be dropped into place. Each of these units is about 38,000 pounds, so a crane was deployed to get that in there. And this is just a picture of the first one being dropped into place. There's the 2 meg breaker right there. There's the chilling unit. There's a tower that goes up on top that's sitting over here on the side. As I said, these are about 38,000 pounds a piece, and they just get dropped on the slab. Bolted. They do get bolted to the slab. They get bolted together. You can see the hitch points here, caulked, sealed, and then released. Proud parents. As I say, you can see the hitch points up here. They actually do get bolted together. This is the second piece of the mechanical room coming in. And then the machine room looks like just any other. It's a small 1-foot raised floor. As I said, we're not pushing air through there, just chilled water. And then they literally just bolt into place. And that was done in about a 5-hour period of time. The thing was powered up by Wednesday. We had a crane come back in on Wednesday, put the chilling unit up on top, and then it looks just like any other build out of an HPC solution. You roll the racks of equipment in and build the system out. So this is, I think, Wednesday when we put the chiller on. So Sunday to Wednesday, everything was done, and then of course it rained. And they came back and then poured that slab. Now, I joke every time that this is what people normally think of the container, and people walked up the first couple, they said, "Oh, that's a wonderful container." I said, "No, it's the building right behind it that is in fact the facility." And then so they poured the concrete slab afterwards for the ramp, and then it was just a question of rolling in all of the racks and then doing all the mundane cabling testing that was required. One of the issues was this is a relatively small space under the floor, so we had to find very small plumbers to do the reconnection work. It really is just it's very tight under there to get in, and obviously the amount of cabling that goes into the system with 1,300 plus InfiniBand cables, fairly congested. I wish Carl actually had done the cabling for us, but just rat's nest of wonderful cabling, because there's this as well as the Ethernet cabling associated with this. There's a substantial amount of cabling, and then just a picture of of the inside with the engineer. And I will skip over the university credits, but the university, and this is just the chilling room. All the pipes for distribution. So I'm going to skip over the university credits and just cut to the last piece. So just some key points. Again, our objective was to deploy a top 50 system because of the constraints that were placed on us, because the project and what the university could accommodate. We really went with this designed data center that was made to order, prefabricated off-site. As I said, the key point was we really drove this down to the time it took us to build, deploy the supercomputer. We got this down to something that the university considered green. 1.1 is what we've seen to date, with 1.2 being the design target associated, and that's based on sort of worst case historical weather and climate data. As I said, this is really key, is leveraging these rapid deployment technologies used by industry that really drove the time, had the expertise at these companies, really drove the time down. And this feedback in between facility and system design really was beneficial from a wide variety of perspective, not only driving the time down, but also sort of getting things right between the two teams. Didn't have to go back and replumb except for one thing that the facility guys misplaced. And it has a fairly long lifespan, about 15 plus years. I expect it to last longer in Colorado. And we built in a 50% expansion factor, so the university has plenty of growing room. It's a relatively easy space to work in and expand into. And low cost, I really can't go into, everybody asks me the precise numbers here. All I can say is that, typically we are looking at data center space, about 10K per KW to dissipate. This is somewhere in the 2.5 to the 5 KW range, so substantially less expensive than traditional practice. And this is just Michael. I give him credit. He was the assistant admin on this. This is our first shutdown of the container, and he was very happy to do this. It didn't fail. And this is where I'm from. This is NCAR in the middle of winter.